Welcome to chapter 20. This chapter talks about electric currents and introduces some other concepts. And we'll even talk a little bit about fuses and circuit breakers before the end. So in order to talk about a current, we need to start out with batteries. So a battery is a source of electric energy. And because it's stored energy, we can refer to it as the EMF, which is a shorthand way of saying the electromotive force. But we're probably going to just talk about the voltage associated with the battery, that stored potential energy. Remember, voltage is another name for the electric potential. So batteries store energy, and when you hook them up to a circuit, you use that energy. Typically, batteries are composed of two different conductors. Those are the electrodes. And then there's some kind of material between the conductors, and that's called the electrolyte. Typically, a single cell battery would have a pair of electrodes and an electrolyte, and then you might have multiple cells comprising the entire battery. There are lots of different types of batteries. They keep getting smaller and smaller as our need for smaller appliances becomes evident. In a circuit, you would see that the battery is symbolized by these two vertical lines. One is short and the other is longer. So the two vertical lines, the longer of the two is the positive electrode on the battery and the shorter is the negative. We'll see more of these diagrams a little bit later on, but for now I'm just introducing individual components. So batteries are two parallel lines, one long, one short. This is just a diagram of a battery similar to a car battery where you can see the individual cells. You'd have the two connectors on it. They have the vent caps. A lot of times automobile batteries these days are sold as sealed batteries, but in the old days, you used to take these vent caps off and actually add liquid to the battery itself. I grew up in Florida, and sometimes your battery would just need a little water added to it in order to last a little longer. All right, so other kinds of batteries, not all batteries look like automobile batteries. Here is an example of probably looks like a AA battery. Notice the green one. The green one just means it's rechargeable. Here's a little 9-volt battery. This is just a little flat coin-shaped battery that you use in all kinds of things, watches and small lightweight items like that. And then this is probably a little lithium battery, could be the kind you see in some cameras or other devices. So we've got just an assortment of smaller batteries shown in the diagram. So let's move on to electric current. So electric current is defined as the rate at which charge will flow through a surface. So it's the amount of charge divided by the time it takes to do it. So if you had 10 coulombs for your amount of charge and it flowed through in 10 seconds, well, 10 coulombs divided by 10 seconds would give you a current of 1 ampere. Current is symbolized by the letter capital I, and it's measured in amperes, but most of the time people never say amperes. We abbreviate it amps, A-M-P-S, when we say it. When you write it, the abbreviation for ampere is a capital A. The abbreviation for ampere is a capital A. And an ampere is a coulomb per second because charge is in coulombs and time is in seconds. Ben Franklin thought the positive charges did the moving, so conventionally we talk about charges going from positive to negative. I don't think that's going to be much of an issue for us. Let's talk a little bit about lightning. So with lightning, whoops, I went too far. I'm bad to do that. So with lightning, we have a separation in charge, usually because of turbulence in the clouds. So in a cloud, you'll have positive and negative charges, but when the conditions are right for lightning, those charges actually separate and the bottoms of the clouds accumulate a negative charge. So that large negative charge on the bottom of the cloud is going to force electrons in tall objects like trees, or if you had an antenna on the top of your house, or even you standing on the top of a hill. The tall objects in an area will have their free electrons repelled by the electrons accumulating on the bottom of these storm clouds. And so those free electrons come down to the ground. But what that does is it leaves the tops of the tall objects with a net positive charge. And so the electrons in the cloud are attracted to the positive charge on the tall objects, and the end result is a bolt of lightning. Now, why am I even mentioning this? Well, it is important to remember that you don't want to be the tall object in the area during a thunderstorm. So this is why they tell you, if you're playing softball and you're out on the field, that if a thunderstorm comes, we all leave, even if the thunder is at a distance, because you don't want to be the tall object. If you're playing golf, you certainly don't want to be the tall object with a metal club in your hand. If you are hiking, you don't want to be on the top of the ridge line, and you certainly don't want to huddle under a tall tree. If the tree gets struck by lightning and you are huddling anywhere near the tree, you too could get struck. So don't stand under trees during a thunderstorm, and definitely don't be the tall object. And this is just a cool photo of a bolt of lightning coming down and striking a tree. Lightning can go cloud to ground, ground to cloud, but it's all about this separation of charge between the bottoms of the storm clouds and the tops of the tall objects in the area. All right, moving on. We need to talk about Ohm's law. We will use it a lot in the coming chapters. So Ohm's law is V equals IR, where V is the potential, I is the current, and R is the resistance. V equals IR. So potential is in volts, current is in amps, and R is in ohms. Electrical resistance is measured in ohms. And we have two ways to write out an ohm. You can write out the word OHM, or you can abbreviate it with the Greek letter capital omega. All right, capital omega looks kind of like an upside down horseshoe. And the reason they don't use a capital letter O is because it looks too much like the number 0. So capital omega is the abbreviation, or you can just write out the word ohm, OHM. All right, so if current flows through a device, the device can act like a resistor. We actually have items that are resistors. They can be made out of wire or carbon or other things. Or you can have a radio acts like a resistor. My toaster oven is a resistor. It's kind of a big one. Any electrical device acts as a resistor in a circuit. So here's just a little photograph of some resistors. These little ones are fairly tiny, and besides normally not having very large resistances, they also can't withstand very much current. The more current you force through a resistor, the hotter it gets, and the smaller the resistor, the less it likes heat. So the little itty bitty ones do not respond well to heat. If you're going to have current flow through a resistor for a long period of time, probably you want a bigger resistor that can stand up to the heat and not get overly hot. You'll notice on these resistors, on the small cylinder ones, that they have colored bands painted on them. Those colored bands actually tell us the size of the resistor. You can see that the bigger ones, they forego the colored bands and they just write the value on the side of it. But up here, we've got colored bands. So how are we going to figure that out? Well, we're going to use the resistor code. And I overshot it again. I really do need to get my mouse and bring it in here. This would make me a little seasick. Shoot, I don't seem to win with this, do I? All right, so the resistor code goes from 0 to 9. A black band corresponds to a 0, and then it goes brown, red, orange, yellow, green, blue, violet, gray, and white. You do not need to memorize the code, but you do need to know how to use it. So on the side of the resistor, there'll be at least 3 colored bands and possibly 4th. If there is a 4th band, it will be gold or silver. If there are only 3 bands, that means your tolerance is 20%. Tolerance is a little bit like thinking of the accuracy, if you will. So it's plus or minus. If it's a gold band, 5% of the value. Silver band would be plus or minus 10%. And if there's no band at all, then the value of the resistor is plus or minus 20% of whatever is given by the colored bands. So you have 2 digits and a multiplier for the 3 colored bands. Let's look at a numeric example. So here is one where we have colored bands. Our first band is black, our second band is red, our third band is green, and the 4th band is silver. Well, silver is pretty easy. That corresponds to 10%. If the first band is black, that corresponds to 0. If the second band is red, that corresponds to 2. And the third band is a multiplying factor that goes with an exponent of 10, and green would be 5. So this would have values of, I don't know if I can insert it over here, down here in the corner, I guess I can. Whoops, they put me in the dark. So this would have a value of, let's see if I can make it happen. So it would be a 0, 2, and then 10 to the 5th. 0, 2, and then 10 to the 5th. So this value, 0, 2 times 10 raised to the 5th power. All right, so that would mean it is 2 times 10 to the 5th ohms, and it would be plus or minus 10%. So that's going to, equal just 2 times 10 to the 5th ohms plus or minus 10%. Well, I can't seem to make it pop up, so we'll let it go. 2 times 10 to the 5th ohms with a 10% accuracy or tolerance for a black, a red, and a green band. All right, let's come down and look at a 5% tolerance for a 10 ohm resistor. So we have to write 10 in terms of 2 digits times 10 raised to a power. And so 10 is just 10, but because we want our times 10 to equal the number 1, we'd have to have a 0 as our exponent. 10 raised to the 0 power is the number 1. 10 to the 0 power is the number 1. So we'd have to rewrite 10 as 10 times 10 to the 0, and 5% is just 5%. So the 3 colored bands, we need a 1 color, a 0 color, and then another 0 color. We need those. So you'll notice up here that 1 is brown, 0 is black, and then the 0 on the exponent is black, and 5% would be gold. So those would be the 4 colors that we would look at: brown, black, black, and gold on that resistor. Suppose we want to know about our resistor with bands of yellow, red, green, and silver. So yellow corresponds to 4, red corresponds to 2, green is 5, and silver is 10%. So we have our 4, our 2, our 5, and our 10%. To turn that into a value, the first two numbers give us the first two numbers. So this is 42, and then times 10 raised to the last digit, that's a 5, so 10 to the 5th, and that would be in ohms, and that would be a 10% tolerance. All right, so to practice, you can work on these 3. And as always, if you need help, ask me for help. All right, moving right along, let's talk about resistivity. We'll be doing a lab using resistivity. So if you have a piece of wire, its resistance, that's capital R, is equal to its resistivity, that's lowercase rho, times the length of the wire divided by the cross-sectional area of the wire. So if you look at this, please remember that the rho looks a little like a P, but normally the tail comes from down below. So let's see if we can draw one just free form for you. So to draw it, I would start below the line, come up and around, and there. And boy, that's a pitiful looking row. But you get the general idea. Start below the line, curl up and around. Yours hopefully isn't that wiggly. I would love to say I can draw a smoother one, but on the computer, maybe not so much. And again, the line is at the base of the circle part of it. So the tail hangs below the line. All right, enough of that. R equals rho L over A. So resistivities are temperature dependent. You would look up rho in a table. So aluminum has a resistivity of 2.82 times 10 to the minus 8 ohm meters. Copper is 1.72 times 10 to the minus 8 ohm meters, and so on. They do depend on the temperature. We're not going to worry about that. We'll assume that most of our experiments will take place at close enough to 20 degrees Celsius so that we don't have to worry with it. So you will notice resistivity is in ohm meters, resistance is just in ohms. And the resistivity depends on what are you made out of, what's the material of the wire. Notice that the longer the wire, the bigger the resistance. Notice that the smaller the cross-sectional area, the larger the resistance. Okay, moving right along. Here are the two equations that allow you to calculate the changes in resistivity if you're at some temperature other than 20 degrees. We're not going to worry with them. All right, we are not going to utilize them. You do need to memorize this equation, R equals rho L over A. And you also needed Ohm's law, V equals IR. But you don't need these two. Okay, moving right along. Let's look at an example. So we know that we have a 10-meter length of copper wire. We want to replace it with aluminum wire with the same diameter. And we want to know how long is the aluminum wire if we want to keep the same resistance. So we know the length of the copper is 10 meters. We know we want to keep the same resistance. So R copper is going to equal R aluminum. We know we want to keep the same diameter, so the cross-sectional area for the copper is equal to the cross-sectional area of the aluminum is just A. And we're able to look up the resistivity for copper and the resistivity for aluminum. We look those up in the table. And we're trying to find the length of the aluminum wire, and we just need this one equation, R equals rho L over A. So we'll start out with that. We'll say, okay, the two resistances have to equal each other, all right? Resistance of copper equals resistance of aluminum. But we know that resistance is RL over A, so RL over A for the copper equals RL over A for the aluminum. And you'll notice these little CUs and ALs are supposed to be subscripts. Sometimes the way the computer types it, it's hard to see that they should be smaller and really slightly below the line. I know it doesn't seem to look like that, but it really ought to be below the line. So smaller and below. And then when we plug in, we know the rho for copper, we know the length of copper. We don't know the cross-sectional area of either one, but we can call it A. We know the resistivity of aluminum. We don't know the length of the aluminum. And again, we don't know the cross-sectional area of the aluminum or the copper. And in fact, because they didn't give it to us, if you wanted to say, let A equal 1 meter squared, that would be an enormous piece of wire and not very realistic, but it would make the math easy. If you wanted to do that, you could. I'm going to just leave it as A, and then we're going to cancel them. But if you want to turn it into a number, just make sure you define it and you say let, so I'll know you're making it up. All right, so because we don't know A, but it's on both sides. If we multiply both sides by A, the A's disappear. And that leaves us 10 times the 1.72 times 10 to the minus 8 ohm meters on the left side. And we've got this 2.8 times 10 to the minus 8 ohm meters on the right. We're going to divide both sides by that. That'll put it in the denominator and leave us with only the length of the aluminum. And when you do the arithmetic, it's 6.099 meters. You probably could have rounded this off to 6.1, but in general, if we're dealing with numbers with at least two digits to the right of the decimal, that's how many I'd like to see. All right, so we have a calculation for the length of the aluminum. Let's look at another example. What length of aluminum wire is necessary if you want it to have a resistance of 4 ohms and a diameter of 3 millimeters? So we know that R is 4 ohms. We know that the diameter is 3 millimeters, but that's the same thing as 3 times 10 to the minus 3 meters. We know that if the diameter is 3 millimeters, the radius is half of that, so 1.5 times 10 to the minus 3 meters. And we could look up the resistivity of aluminum in the table and come up with 2.82 times 10 to the minus 8 ohm meters. They want us to find the length, and we have two equations, R equals rho L over A, and the one that I didn't write down earlier, because I assume you all remember that the cross-sectional area is equal to pi r squared. A equals pi r squared. So the first thing we need to do is calculate that cross-sectional area since they didn't give it to us. So A is equal to pi r squared, plug it in, pi times 1.5 times 10 to the minus 3 meters, and that has to be squared. When you do the arithmetic, we come up with 7.0686 times 10 to the minus 6 meters squared. Normally, we don't round off very much early in a calculation because it'll throw the answer off. All right, we can find L now. We know that R equals rho L over A, and we know R, and we know rho, and we know A, so we can find L. R equals rho L over A, so 4 ohms equals 2.82 times 10 to the minus 8 ohm meters multiplied by L, and then divided by 7.0686 times 10 to the minus 6 meters squared. When you do the arithmetic, when you take this denominator and multiply it by 4, and then divide that answer by the 2.82 times 10 to the minus 8, you should get 1,002.64 meters. If you don't, you need to ask me for help. It is a long piece of wire. And that gets us to superconductivity. No calculations for us in superconductivity, just a little bit of discussion. So superconductors are materials whose resistivity and resistance approach zero at specific temperatures. The transition temperature, or the critical temperature, is the name we give to the temperature where a material becomes a superconductor. Mercury was our very first superconductor. And right now there's research being done just all over the physics world on the goal being to get a room temperature superconductor. Why? Because if we can cut down on the resistance, we can cut down on the energy loss. And we could have conductors that were very, very energy efficient. So we've got all kinds of stuff going on. They really have been remarkable. The latest research has given us a superconductor that conducts at 57 degrees Fahrenheit. That is incredible. The problem with it is it requires an enormous amount of pressure in order to do that. A pressure that's equal to 2,640,000 times the pressure of the Earth's atmosphere at the surface. So this is not practical right now. The earlier superconductors were ceramic compounds, and unfortunately they required really cold temperatures. So we're still working on it. I've already said the reason why we care is you'd get more efficient conduction, so better power lines, smaller motors and generators would be better for electric cars. There's just all kinds of cool uses for it. One of the neat things about superconductors is something called the Meissner effect. If you have a rare earth magnet and a superconductor disk and you make the disk really cold, what it does is it alters the magnetic field in the disk, and it allows this really powerful tiny magnet to hover over the superconductor disk. And so that's just a little neat trick. I don't have any liquid nitrogen, so we will not be playing with the Meissner effect, although it would be neat. There are lots of videos on YouTube. That gets us to electric power. Electric power is the same, really, by definition, as mechanical power. Power is work divided by time. So with electricity, if you do the appropriate substitutions where V is equal to W divided by Q, and you end up, and current is equal to Q over T, you can rearrange everything. So we could start out by our traditional definition of power, and in electricity, it converts to P equals IV. So we had V equals IR, we've had R equals rho L over A, and now we have P equals IV. P equals IV is Joule's law. Some people just say, oh, PIV, P equals IV. Power is in watts, current is in amps, and V is in volts. All right. So let's talk about what is a kilowatt hour. If you've ever paid your power bill, you may have noticed it's not Duke Power anymore, it's Duke Energy. And that's because the electric companies bill you in kilowatt hours. And what you're actually ending up buying is electrical work. And work is measured in joules, just like energy is measured in joules. So you're buying energy from it. I think we will stop right here and we'll pick up with alternating current in the next video.